So I'm here on a beautiful day with underneath beautiful starlight, our own sun, which is so precious. We don't realize how precious it is, as is our Earth, at the University of Copenhagen. At the title of the conference is, you tell me, Julie, what
Are
is,
we a unique species on a unique planet?
are we a unique species on a unique planet? Having a senior moment. Anyway, we were discussing pulsar planets, which have been kind of given the short shrift over the decades. They were the first extrasolar planets ever discovered in the radio spectrum. And Julie, you are an evolutionary biologist by training, but you have an interest in these planets because of the extreme
Exactly. It's
of the extreme possibilities that they represent for both the potential that they were planets at some point, like maybe even like our own, or they are planets that formed after a star that's gone supernova and it has turned into a fast spinning neutron star, i.e., a pulsar. So, have these, if my memory serves me, they were first detected in 91, 92 by
it's true.
Alex Wolshin and Dale Frail. So, tell us, do you think these pulsar planets have been neglected by the astrobiology community?
They definitely were because they don't tend to be appreciated as habitable environments for obvious reasons. Their environment must be truly exotic and very likely not habitable at all, at least for life as we can imagine it. But that doesn't mean that they are not interesting for astrobiology, because being able to know more about them, to characterize them, would yield tremendous insights into exoplanet science in general. These planets must be extreme and weird. For the first system discovered by Wolfson and Trail, it's unlikely that the three planets that are there survived the supernova explosion. So they should be formed afterwards, either from the radioactive heavy infalling dust after the star has gone supernova, which would make them truly extreme objects, which might yield interesting insights into geophysics of such planets. How do they behave? I mean, do they have magnetic fields? How do they lose heat? Are they magma oceans through and through? Are they heated also by induction forces, which has been considered for planets of M dwarfs like TRAPPIST-1, and for planets of white dwarfs, but no one has looked into it for pulsar planets. And there are many other formation scenarios that have been proposed, but we can't tell which is the actual one. How did they happen to be there? Because to be able to do that, we need to characterize them, which is seemingly impossible at the moment because they are extremely far away. The closest planetary systems around pulsars are hundreds of parsecs, which is several thousand light years away. So they are extremely far, and their star is peculiar because pulsars are tiny. They are like 10 to 20 kilometers across. It's like a city on Earth, and they are extremely fast spinning. They are practically invisible in the visible part of the spectrum because they are so tiny, so faint, so that we can see them in the radio, and we can detect pulsar wind around them, this wind of really energetic particles, which we still don't know a lot about. So also being able to see how it affects the planets would be great.
But let's say that, for argument's sake, that these are not planets that formed post supernovae, but planets that were already there, that could be like our own dear planet here, around a sun-like star that just happened to go supernovae. Of course, it would have to be massive enough
Yeah,
to go
it would be
supernova,
more massive,
more
yeah.
massive than our own our own sun. But suppose there was life around potentially before the star went supernova.
It would have very little time to evolve because such stars only have millions or tens of millions of years to go on the main sequence before they go supernova. So
this would be
it's not impossible.
So you're saying
but
this would be
it's-
an OB or A star, most likely.
Yeah.
Okay. So so there's no possibility of life ever being on these planets, but
Seems very unlikely.
But they might have had time to develop a crude atmosphere, is what
Yeah.
you're saying. But still, we have a dearth of information about these pulsar planets, right?
Yes, we can constrain their orbits and mass from timing the radio pulses from the millisecond pulsar, but we don't know anything more. It would be great to know about their composition and whether they have or indeed can have at all any atmospheres, and whether they have magnetic fields. Any of that could tell us more about how they formed and how they can tell us more about, let's say, less extreme exoplanets that we could find around more sun-like stars on the main sequence.
But the fascinating thing is, if you imagine that you had a normal star, even though it was a massive star, before it went supernova, there was a planet around it. Maybe it had a crude atmosphere, had time to develop a crude atmosphere. All of a sudden, the thing goes supernovae. The planet, whatever it is stripped of its atmosphere, and literally, if it's in close enough orbit, torn apart by the massive gravity of the neutron star spinning, as you described. And then basically, you have no visible light. The planet itself is dark. The remnant star, the neutron star, is dark. It's a very creepy kind of dark system.
Yeah.
I mean,
you can imagine a planet composed of largely heavy radioactive elements, maybe with a faintly glowing magma ocean on the surface. Maybe if it had some thin atmosphere and magnetic field, there could be aurorae illuminating the surface of the planet, and maybe you would be able to see this very, very faint source of light, the pulsar in the middle of the system. But it would be nothing like the planets we have in our own system. And again, there are several known planetary systems of pulsars. Each is wildly different. There is the one discovered by Wolfchan and Frail, which has 3 exoplanets of roughly Earth-like mass.
Mm-hmm.
So they are likely rocky planets or like metallic planets. But there are also very massive planets orbiting pulsars, both on faraway orbits and so extremely close that they should be torn apart by the gravitational forces.
But they're not.
They're not. So
They're not. We don't know why.
yeah.
Okay. So, and hopefully the square kilometer array might yield, some new characterization of these planets. Maybe the extremely large telescope in Chile when it comes online later on in the decade. But it's not going to be easy. So, Julie, thanks so much. Julie Novakova. From the Charles University in Prague, the Czech Republic. Beautiful city. Thanks so much for taking the time to talk to me.